Hello, Djordje Romanic here. Welcome to Fundamentals of Weather and Climate playlist. We studied in great details dry adiabatic processes and moist adiabatic processes. Now the final question is, how does air temperature changes during dry adiabatic and moist adiabatic ascent in the atmosphere? Let's discuss it. As we are doing it, please make sure to like and subscribe. Please leave a comment. I read all of your comments and I really appreciate when you leave a comment. Let's see how temperature changes with height in dry and moist adiabatic processes. If here is temperature of an air parcel and here is height, Z. We start from height Z equals 0. So here is Z equals 0 and we have this small air parcel. Now, in this small air parcel, remember, we have water vapor, that's green. And now we lift this air parcel. When we lift this air parcel to this height, whatever it is, let's match it over here. The air parcel will expand and temperature will decrease. It will expand maybe to this size. Up to this point, there was no condensation, so the process is dry adiabatic. In dry adiabatic process, if we started from this temperature T0 at the surface, in dry adiabatic process, temperature changes with height like so, perhaps. And I'll tell you exact value in few minutes. But this is how temperature conceptually changes with height in dry adiabatic ascent. But now, this water vapor starts condensing. Because at this level, perhaps temperature is low enough so that saturation pressure is equal partial pressure, and we have some saturation. So we still have water vapor, but less water vapor than here because some of it's saturated. That means at this point, now this is beautiful part, we are connecting concepts from all previous videos. At this level, you know from my previous videos that partial pressure of water vapor is equal saturation vapor pressure at this temperature T, local temperature at this level. Because condensation releases heat, this condensation released some heat, what we discussed in the previous video, and in adiabatic process we assume that heat stays in this parcel of air. When this parcel of air continues rising, rate of temperature drop with height will be less than rate of temperature drop during dry adiabatic process. Because during dry adiabatic process, there was no this release of latent heat of condensation. But during moist adiabatic process, we have this release of latent heat of vaporization. So the purple line now means from this level up, the temperature in the parcel of air is still decreasing. I hope, yes, it is still decreasing. But the steepness of this line is more, in other words, the temperature is decreasing less with height than what it was during dry adiabatic process. So this over here is dry adiabatic. And this over here is moist, saturated adiabatic process. Now let's keep moving this air parcel up. So at later it might end up being here, volume increased. And let us now assume that all water vapor during this ascent condensed, and there is no more water vapor. Now we further, as we discussed in the previous lecture, we don't have to do it, but we can also remove these condensates. That's what we discussed in the previous lecture if we want to define equivalent potential temperature. Anyways, at this point, notice that there is no more green dots, no more water vapor. And the air parcel is at this height. So, up to this height, the ascent was moist adiabatic. If this parcel of air continues now going up, it will be even larger at this height over here. But is this now ascent dry adiabatic or moist adiabatic? Well, it will reverse back to dry adiabatic. Why? Because there is no more water vapor to evaporate. So, hereafter the change of temperature with height is exactly the same as this line. Well, I made it. It should have the same steepness as this line. Let's say like this. Okay? So this is again dry adiabatic lapse rate. I hope this is clear. What I am trying to tell you is that during dry adiabatic ascent, drop of temperature with height is much higher than during moist. And I forgot T over here. During moist adiabatic ascent. That's because during moist adiabatic ascent, we have release of latent heat of condensation, which we do not have during dry adiabatic lapse rate. And this latent heat of condensation offsets some of dry adiabatic cooling that happens otherwise. Now, the question is, can I tell you numerical values for these lines? Can I tell you what is the rate of change of temperature with height? The answer is yes. Of course I can. I can tell you everything. I know everything about atmospheric sciences. Dry adiabatic lapse rate is an easy one. We know, well, let me write. You know, let me use black. First principle of thermodynamics was that delta Q is equal Cp delta T minus alpha, and alpha is 1 divided by density, delta P. And the process is adiabatic, that means delta Q is equal to 0. This is very important. If the process is not adiabatic, then none of this works. We are looking into adiabatic processes. If you set equal to 0, and you divide the right-hand side by delta Z, because we are interested in delta T, delta Z. How change of temperature with the change of height. How temperature changes with height. So you would have to divide this by delta Z, and then use equation of state. You remember equation of state from my previous videos. You substitute equation of state, you mingle around, and you get that this during dry adiabatic processes, dry is equal G divided by Cp, negative. G is gravitational acceleration, 9.81 meters per second squared. Cp is specific heat at constant pressure of air, dry air, about 1004 joules per kilogram per Kelvin. So this numerical value is equal minus 9.8 degrees Celsius or Kelvins per kilometer. I mean, how can I make it so important? This is extremely important result. Extremely important result. So important that I want to make sure it is in red. So this tells us that for every kilometer, this parcel of air rises its temperature will drop for almost 10 degrees Celsius. And it is very exact. It's not negotiable. It is 9.8 or almost 10 per kilometer. Why is it so exact? Well, it is exact because the process is adiabatic. There is no heat being added or removed, and the composition of the parcel of air doesn't change. So it is always 78% nitrogen, 21% oxygen, and whatnot. So this has to be constant, therefore. Now, let me erase this. I would like to introduce some shortcuts that we use in atmospheric sciences. You see, we say, and I will use this in my next videos, this dry adiabatic lapse rate is usually indicated as capital Greek gamma d, and it is equal negative delta t delta z. And because we define it with negative, that means then that becomes positive g divided by Cp, and I just told you it's 9.8 degrees Celsius per kilometer. So, dry adiabatic lapse rate, gamma d, is defined as negative delta t delta z. Now we go to moist adiabatic lapse rate. And you ask me, is there equation for moist adiabatic? Can you tell me this value for moist adiabatic lapse rate? Of course I can tell you. I can tell you everything I'm telling you. But the thing will get a little bit more complicated. For moist adiabatic lapse rate, we usually call it gamma m. That is still minus delta t delta z, but during moist saturated processes, and that is equal. This one was g divided by Cp. This one is also g divided by Cp, except a little bit more complicated. Here we have 1 plus Lv, latent heat of vaporization, 2,500,000 joules per kilogram of water, times Rs, saturation mixing ratio, divided by Rd, gas constant of dry air, 287 joules per kilogram per Kelvin, temperature, T. In denominator, we have 1 plus Lv squared Rs divided by Cp, this same Cp, Rv, gas constant for water vapor, 461 joules per kilogram per Kelvin, temperature squared. This, you say, oh my God, this is much more complicated than this. You are very right, this is much more complicated than that. But we are learning through last few videos that moist adiabatic processes are much more complicated than dry adiabatic processes. It's not because of me, it's not my fault, that's how the nature works. Moist adiabatic processes are much more complicated than dry adiabatic processes. I'm saying it now almost in every video, I'm not deriving equations here. So you see, I didn't derive this, I'm just telling you how it is. In my advanced playlist, I will derive this step by step if you want to know rigor behind it. But let's analyze this. Because the question, very important question, is gamma m larger or smaller than gamma d? If you don't know much about mathematics, you would think it's larger because look, I'm multiplying GCP, which is the same as this, by something, so maybe it's larger. Well, it's not larger, it's smaller. Because this denominator for moist adiabatic processes grows much faster than numerator, that means this is below 1. This mess over here is a number that is less than 1. So that means when I multiply GCP, I'm gonna get number that is less than 1. So that means that this is smaller. And that makes sense. This is what I just told you here, that during moist adiabatic processes, temperature decreases slower at smaller rate with height than during dry adiabatic processes. Why? Well, because during moist adiabatic processes we have release of latent heat of condensation, which we do not have during dry adiabatic processes to offset dry adiabatic cooling due to expansion of an air parcel. While this is very big mess, you can also see that if Rs, which is equal mass of saturated water vapor divided by the mass of dry air, if this is equal 0, well, in other words, if there is no water vapor in the parcel of air, if there is no water vapor, then this whole term is equal to 1, and indeed moist adiabatic lapse rate is equal to dry adiabatic lapse rate. 1 plus 0 is 1, 1 plus 0 is 1, 1 divided by 1 is 1, so GCP, GCP. So if Rs is equal to 0, gamma m is equal gamma d. That makes perfect sense because there is no water vapor to condense. In the next video, we will discuss the concept of stability. You see, this is how the temperature of a rising parcel of air changes or descending parcel of air changes. But what we want to study is also how does that change of temperature correspond to ambient temperature at a given height. Because you have parcel of air moving up with respect to stationary atmosphere. How does rate of temperature change matches or not matches the rate of change of temperature in the ambient static atmosphere? And that will reveal the concept of static stability of the atmosphere. To properly understand that, make sure you familiarize yourself with this concept. This is, oh yes, sorry, I am finishing video, oh my god, but I didn't tell you some values of this gamma m. Professor Romanic, you say. Of course I will tell you, don't worry. Because I told you that gamma d is 9.8 degrees Celsius per kilometer. You are asking me, can you tell me values of gamma m? Values of gamma m are not fixed because it depends on Rs, how much vapor I have in the parcel of air. So I can give you typical values. And typical values, if you have very moist tropical air, and we saw in my previous videos on humidity that tropical air is very moist air, then in that case, gamma m is usually between 4.5 to 5 degrees Celsius per kilometer. 2 times smaller than dry adiabatic lapse rate. If we have mid-latitude air, which is pretty much air I have here in Montreal, then gamma m is about 5 to 6.5 degrees Celsius per kilometer. Why is it higher value? Because we have less water vapor than those folks in tropical region. And if you go to polar, very cold air that can contain much less water vapor than mid-latitude and moist air, then gamma m really approaches gamma d because there is very little water vapor. In that case, gamma m is almost 9.8, maybe 9 degrees Celsius per kilometer. Now I told you everything. You can copy this, go to your professor and brag how you are amazing at knowing moist adiabatic lapse rates in the atmosphere, and they will be impressed because moist adiabatic processes are not for birds. They are much more complicated than dry adiabatic processes. Please make sure to like and subscribe and share this video, and until next lecture, goodbye.